we're going to go ahead and talk about the importance of good soil sampling. And I think with almost no other type of sampling that we do in our work, soil sampling truly follows the garbage in, garbage out principle, because good results always begin with a good sample. So we're going to talk about the basic principles of good soil sampling as we go along, and I'll just briefly touch on a couple of things here on the outset as kind of an outline, and then we'll take each one of them in turn and discuss them a little bit more in detail. So the first area we'll talk about is looking for representative areas to sample and settling in on our sampling pattern and locations. The other thing, the other major basic principle is getting good physical averages of conditions, using the proper tools, the proper compositing, and not only getting the right number of samples in the composite, but then doing adequate, proper subsample preparation for laboratory submission, cleaning, minimizing cross-contamination as we take samples across a field and so forth. The other major area that we want to focus in on is appropriate sampling depth. And that will vary depending on the target analysis. And so we're looking at preventing false readings. We're looking at preventing any kind of weighting or diluting of results that might happen from missampling depths, and including zones maybe that aren't a target area for the kind of analysis that we're trying to accomplish. And then the last major area that we'll cover before we open it up to questions is then proper handling of the samples once we've taken them, to ensure that we don't get any unwanted changes in soil conditions prior to analysis. So that's kind of an overview and outline of how we're going to take this approach, and then we'll look at each one of these different areas a little bit more in detail. So in terms of representative area, there's all kinds of things that can introduce variation or variability in the field. We're familiar with the concept of spatial variability, but we can tolerate some spatial variability and account for it in our sampling patterns and still have really good samples. But there are some situations where we want to pay attention to differences that are taking or overlaid in a given area that we might be sampling, so that we can account for those from the outset. And some of those kinds of things might be changes in soil type throughout the area. And we're talking about significant changes, and we'll talk about what that means here as we go along. But if you get a full soil series change within a field, as it might be mapped by NRCS in that particular area, you may want to consider some differential sampling. We'll talk about that. Plant community differences may put some overlays on our sampling that we want to pay attention to. And this is particularly for those of you that might be interested in range sampling, in cattle production areas and other things across the state, where we're wanting to look at soil differences and nuances to nutrient management or chemical properties or whatever it might be. Here a while back, Randall and others had me involved in the Society for Range Science in the Utah chapter conference, and I did a big presentation on range soil sampling, and it's a little bit different than it might be for agronomic and horticultural settings. And so if you're interested in that presentation and you would like maybe a copy of the slides that went with that, let me know and I can make them available to you. We won't deal a lot with that, but if plant communities change significantly in an area, it probably means that there's some baseline soil differences that need to be accounted for and sampled separately. Topography is another difference in a field that we need to pay attention to. I say greater than 3% difference in slope. That's the NRCS's separation between modifiers on soil series. And so a soil series will get a modifier based on slope, 0 to 3%, 3 to 6%, and higher. And so that 3% difference is often typically used as the separator for significant differences in soil conditions that could end up confusing a sample across a field. We may have to take those into account as well. And then differential management. This happens quite often in situations like the following, where we maybe had differences in cropping in a given field. You might have had a crop on half the field, different crops on half the field. One part of the field might have been in fallow the previous season, et cetera, those kinds of things, particularly in dryland regions. And so we need to take into account the previous cropping patterns to know if there's going to be a significant difference in management in that field that we have to account for. Fertilizer, manure application, it's not uncommon for a grower sometimes to have manure that they're trying to dispose of, and they may apply it and they only have enough to really apply it on a part of their field. Any kind of differential application of fertilizer, like in a banding situation, a placement for phosphorus or whatever it might be.
Scratch paper.
What'd you say?
Is this just scratch
Yep,
paper?
that's your scratch. And if you need more, I got plenty.
Boyd, could you mute your mic, please? Thanks. Anyway, previous cropping, fertilizer placement, and irrigation. I know that in many cases, like under a pivot, you may have half the field in a rotational crop and half the field in alfalfa or something like that, where you have differences in irrigation management too that might be overlaid at any given time in a field that could introduce variability. Furrow patterning is also an important aspect, or if you're in a drip irrigation system, drip line placement and things can affect the way salts move from the furrow on into the bed or away from the drip line and into the crop row and those kinds of things. And so if we're sampling specifically constantly in a furrow or on a bed or on a shoulder of a bed or within the drip line, we can introduce some patterning to our samples that's undesirable. The other thing we want to watch out for are anomalous areas. And what are we talking about there? We're talking about a lot of times you'll find that in a field for a temporary period of time, you may have a corral or a temporary pen that might have been set up. This happens a lot. I know out in Box Elder County, where you've got a lot of livestock and cropping going on. Folks will bring their livestock down from summer range and they'll graze them on some of the fields, and they'll set up exclusions, or they'll set up pens and other things for the animals on fields. And that can introduce some anomalies in terms of manure deposition, trafficking and things in the field and so forth. Feeding and watering areas, old haystacks, fertilizer storage areas and things that might have been removed. They can also be just real point, small area anomalies sometimes within a field that we should take into account when we're sampling. We don't want to artificially weight a result by taking samples from areas like that that are vastly different from the rest of the field condition. And then obvious high, low spots, salt seeps and other things we typically try to avoid in our sampling patterns. For the most part though, what we're really looking at is trying to develop a good physical average that'll give us a basis for future management. And based on what that future management might be, will also help dictate what kind of sampling pattern that we decide, even if we don't have a lot of these anomalies or large differences in topography or other things in the field. And we'll talk a little bit about that here as we go along. So if we're talking about just capturing basic field variability, Often the recommended sampling pattern will be something like a zigzag throughout the field. Here you can see a field that's, we got an outline here of the field that has some internal lines that are kind of showing where some of the variability might be. This might be differences in soil type or whatever the field variability might be, a little bit difference in texture or what have you. And you can see that with a zigzag pattern, even if it's fairly moderate variability within that field, a good zigzag pattern starting off in random locations and moving through the field will help capture a lot of that variability. And we don't artificially weight one sample area over another when we're doing so. We'll talk about the numbers of samples here a little bit later and how many we would introduce into a pattern like that in a field. And so this would typically be, you know, if we're in a fairly uniform field, even with a fairly moderate amount of variability, would be a reasonable sampling pattern to undertake in order to incorporate that variability into the physical condition average that we're trying to create from that field with our sample. I'm going to stop sharing here for a second because I want to go into another application called Soilweb, and I know that many of you are probably familiar with it. Soilweb takes the NRCS's data and puts it in a Google Earth overlay so that we can evaluate soil series maps and things like that for given areas. So I'm going to stop sharing for a second and reshare my Google Earth so that we can see a couple of interesting examples. So here you have your basic Google Earth, and over here on the left-hand side, you can see this Soilweb layer that I've downloaded from the California Soil Resources Research Laboratory at UC Davis that produces this particular application. And you can just stick it in your own Google Earth, and it'll put all of the soil series right into the system. I'm going to take us first to a place that we're all probably fairly familiar with, and that's the Greenville farm here on campus at Utah State. We'll fly on in to that particular location. And once it settles in on the farm, it'll populate, as you can see here, it'll populate the soil series map. That's the yellow outlines that you see there. So this is the Greenville farm and some of the associated properties in and around it. This is the soil organic vegetable farm that Jennifer works with, and things not too far south of the Greenville farm. And what you'll notice here is that the soil series is very uniform across that entire area. We're looking if on average across that whole area, pretty much exclusively the Millville silt loam of a fairly narrow range of slope. And so doing a zigzag type pattern in a field, getting a good composite physical average sample is a reasonable sampling pattern to undertake in this particular area. But let me take you just not more than maybe 7 miles away from here to a fairly new farm that we have here at Utah State, and that's the Godfrey farm. It's a little dryland research field that we have out in Clarkston, just south of Clarkston, that we've been doing a fair amount of dryland research on here, and we'll let the soil series map resolve here. And you can see a very different condition out on this particular farm. Lots of variability across this kind of triangular shaped area, which is the Godfrey farm. It's about a 30-acre piece of ground we have here for dryland research. If I click into any one of these, you can see what I'm talking about when I'm talking about topographical differences in soil series. So up here in this particular area, in the lower right-hand corner of the triangle, we're in primarily an area of Menden series. 95% of the soils are the Menden series, from 0 to 3% slope. But if I just go a little bit beyond that, just a few hundred feet from this area here up into the upper part of the field, the northern end, then we get in the same soil series, but now we're in the 3 to 6% slope category. And so we've had a significant difference modifier in the soil series here on slope. And that's going to make a big difference to the soil physical and chemical conditions of that area based on the slope. And then just over here to the western edge of the field, it's the same soil series, but you'll notice something really interesting about that. It's mostly Mendon series, but we've got it into a 6 to 30% slope and highly eroded area on the farm. And so if I just do a standard zigzag pattern sampling across some of these differences, then I'm going to perhaps disproportionately weight a sample to one of these very different conditions in the soils. And so a differential sampling pattern in an area like this, where I focus on areas within the field that are very different with respect to slope, is topography one of those things that we take into consideration, then I'll do a much better job of getting what the average conditions are within those areas that are significantly different from others. And we'll talk about some of these kinds of differential sampling patterns that we might employ. We use this particular case study a lot. This is actually in one of the fact sheets that we've had for a long time in the Utah Fertilizer Guide and so forth. It's a really good case study right here in Cache County. This is a pasture. A lot of times we'll be sampling in pasture areas as we have opportunity to interact with even small and urban farms and things like that as well now. What you see here is a field that's, these are on 10-foot spacing grid. So you got each one of these ticks is 10 feet. So you got 250 feet by about 100 feet. On this pasture. So each one of these circles represents about 100 square feet of area in that particular pasture. So we're on a 100 square foot grid here. The smallest dots in the graph represent the Olson soil test for phosphorus of 0 to 3 parts per million. Very low test phosphorus in that particular field. The large circles, however, that you see, the largest ones, are in excess of 20 parts per million phosphorus, which would be well into a sufficiency condition for phosphorus for pasture production. If we look at the percentage difference across the field of the various conditions with respect to phosphorus content, 14% of the field is severely deficient. About 36% of it, a little over a third, is moderately deficient, but over half, about half of the field has no need at all for additional phosphorus. If we look at where the access to this particular pasture is, it's right up here in the upper corner where the gate is. And if we're lazy about our soil sampling, if we just come into the field and we come a few feet, maybe even a few tens of feet into the field thinking, well, we're into a representative condition, and I sample up here in the upper left corner, I'll find out that I'm in a condition that probably doesn't need any at all. So in that case, we'd have no need for phosphorus here, but then in these areas, I'd have a very high need for phosphorus management. And so we can see that, potential differences, and this is a result of animal feeding and watering patterns within this particular field and the deposition of manure from the grazing animals in that pasture that introduced that particular difference. And that's going to greatly depend or dictate the kind of success I'll have in not only getting a good laboratory recommendation for management needed in the field, but comparison year to year, I might end up taking a sample in a different area, and I'm going to wonder why the lab gives me such a different result in a subsequent year than it had in a previous year. And a lot of times it's because we have these patterning overlays that we haven't taken into account in our sampling. So how do we deal with field variation? one of the ways that is recommended in dealing with field variation sampling is using grid sampling techniques. Grid sampling techniques can help us get a really good broad picture of what's happening across the field in terms of differences. But this would not be desirable, for instance, if we were going to be compositing. So something like this would be used if we want to get a really good feel for what point measurements are within the field of the differences across the area. So in a grid sampling, if I were to take a sample at each one of these dot locations and then analyze it separately, I would get a point value of whatever the soil analysis is. And then I can look at the way that that varies across the field, and I can map the actual differences that I have across the field. We can get physical averages in a couple of different ways. We can get them just by compositing all of our samples in one and having a physical average that way. Or I can get a numerical average if I were to sample like this on a grid and analyze each of these samples separately. And then I can mathematically average the samples, not only over the entire field, but then over different management or overlays of different soil types or whatever the variability might have been caused by. If we look at using a composite sample, for instance, where I just take all of these point samples and I combine them all in one physical average, you may say, well, I've done a pretty good job of sampling within all of the different areas. So I have representative samples, or I have samples that represent various parts of the field and the changes that are taking place there. You can say, well, then that's probably a pretty good composite sample, because I'm incorporating all of the variability in one, and it gives me a pretty good physical average. Well, that may or may not be the case. In this particular case, the white dots indicate those that were taken in this orange area, and that may be a different soil type or whatever that variability is. That's 30% of the total number of samples. 30% of the total number of samples, but that orange area only represents about 20% of the overall field. And so if I'm saying that a grid sample in this particular case and compositing that gives me a good physical average, I'd be wrong in the sense that I've artificially weighted the effect of that particular anomalous area into the overall result. It's weighted 30% in the overall sample, when it really is only representative of 20% of the field. And so stratified sampling or targeted area sampling then would be the recommended pattern in something like that. So I don't artificially weight the impact of that anomalous area on the result. Particularly if I'm going to try to manage this field a little bit differentially as well. I want to know what's going on within that area that's different, that different soil type or whatever that might be, in terms of the way I'm going to manage it in the future. Am I going to put more inputs into it? Am I going to irrigate it differently? Am I going to plant it differently, et cetera? You'd want to know what's going on within that area specifically. What about banding and fertilizer placement conditions? We get a lot of questions about that. If you go in and sample a field where you've had fertilizer placement performed in the past, and you focused on a regular patterned sample like a grid sampling program, you may overlay directly on or off where the fertilizer had been placed. And so you may artificially inflate or deflate the overall average condition based on either hitting or not hitting repeatedly those banded areas. And so when we're dealing with a situation where we're going in sampling where in the past banding or fertilizer placement has been done, and we know the location of the bands, then we can ensure the fact that we have an even mix of samples both in and out of the banded areas, so that we get a reasonable average condition of fertility, or whatever the chemical analysis is that we're performing on that particular field. But a lot of times we'll come into a situation where we don't know exactly where the bands were. It's not obvious to us. We're not really sure. Then we can do what we call paired sampling, paired random sampling, where we come in and we take an initial random location and we take a physical sample. But then we take a pair sample with that, where we take a companion sample that's 50% of the band spacing away from that first location, but perpendicular to the placement of the bands. So if the bands are running, north-south, then I would take a random location, and then 50% of what I know that the band spacing was, I would take it perpendicular or east-west of that particular location. So I'm ensuring the fact that I get this paired companion sampling, where I'm either without or nearly within at all given times where the band might be. And then both of those companion samples go into become a single observational point. So they become a single point sample for a composite then from the entire field. And we talk about that. So this would be one of maybe 15 to 20 locations we would take within that sampled field. You'd have those two companion samples spaced 50% of the band spacing apart and perpendicular to the band placement, which helps you account for the potential patterning that can come from banding in a given location. So we've talked about, for most cases where we don't have a lot of variability, going in and taking a random start point and then zigzagging through the field will help us capture a lot of just basic variability. If we do have a lot of differences that we want to account for in the field, we can grid sample and then analyze specifically at each point. That allows us then to kind of map the conditions and determine where areas might need specific attention. Or we can go in and do some stratified sampling, where we know where that anomalous area is, and we sample it separately so that we get a physical average of conditions within that area specifically that we can then use to target our future inputs and management. In the case of banding, we've talked a little bit about the nuances with respect to that type of patterning in the field. This kind of sampling with banding placement of fertilizer and other chemicals would also be appropriate in a situation where we have drip irrigation or furrow irrigation or other things, where we can introduce a very specific pattern of accumulation of salts, for instance, in the shoulders of the beds, or differences in leaching that might have taken place below a furrow compared to in the middle of the bed, and those kinds of things. So this same random companion sample can also be effective in that type of patterning as well. So also important to good physical average, besides sampling location and field variability accounting and so forth, is using the proper tools. And I know Jody and I have had a lot of discussion about this in the past in our recommendations on things. With today's technology and the fact sampling technology, and the fact that they're so readily available at cost that is reasonable, coring tools are really the preferred sampling tool for taking soil samples, for a number of reasons. And I'll be stronger than saying actually preferred, and say really this is the most accurate way of taking soil samples, because we have a constrained subsample volume that we get with these coring tools, very uniform from location to location in the field. We can mark them very accurately to make sure that we're getting right to the very depth that we're interested in. And with these kinds of sampling devices, we don't get the side scraping and other things that can happen in a borehole with, say, a bucket auger or a Dutch auger or a flight auger type sampling tool, or a spade or shovel. In fact, spade and shovel sampling is really not recommended for the most part because of the real variability we introduce in terms of the volume of the subsample, the accuracy of the depth of sampling, and so forth that we're able to accomplish with a spade or shovel. Also, part of your tools when you're creating a composite sample within the field is using appropriate containers. So plastic buckets are advised when we're depositing subsamples from the various locations we're taking them. We want to be careful of metal buckets that we might be using, particularly galvanized metal buckets, which is not uncommon that we would have that we might be using in a field situation or a farm location. Galvanization coatings, nickel and zinc and others that are used are potentially contaminating to the samples. So plastic buckets are really recommended for that. And then a hand trowel or something that you can really break up the subsamples that are taken with the coring device and thoroughly mix them together so that you can get the kind of composite sample uniformity that you desire. And I'm going to throw in here an important aspect, and something that we don't often take into consideration, but they're so readily and inexpensively available. Riffle splitters, we'll talk about what they are and how they work, are really useful in preparing a good well-mixed composite sample where you're reducing the overall volume of what you've taken in the field down to something that you're going to submit to the laboratory, so that you don't artificially weight that smaller subsample to a given part of the composite sample that you've taken. Coring tools, there's so many of them that are available out on the market. It just is just a quick perusal of the internet and what's available. These vary anywhere from a half to an inch in diameter. Open split tube core samplers like this that can be easily inserted into the ground at the surface or the depth that you want to extract the sample from. They are created so that they pull out a very uniform volume of subsample. Some even are equipped with aids to inserting them and extracting them from the soil. This particular one has a plunger in it that allows you to quickly express the sample from the coring tube into your bucket, so forth. So there's lots of different types. We won't cover them all. But these are really very reasonable. Most of you have them, I'm sure, in your extension offices and so forth, and programs. This is an AMS probe. It's about a 24-inch probe. $60 gets you a really highly accurate, well-machined, robust sampling device there. And really, these are the most accurate, most preferred way of obtaining uniform subsamples in any sampling program. But we do have augers available to us, and sometimes these introduce some advantages, particularly in things like really gravelly sample areas where we have a hard time getting a coring device into the ground at depth. Really sandy soils that don't stay well within a sampling tube as we extract it. Really sticky wet conditions that may not go easily into a core sampler, or even in situations where we might be interested in sampling frozen soils. We don't do that very often, but flight augers in particular can be very useful in that. We do need to understand that this is a very aggressive, very disruptive sampling method. These are coring tubes, of course, and they were not applied, but flight augers, bucket augers, Dutch augers, like you see here in D, are very disruptive of the soil itself. Hard to determine exactly what depth you're at when you're taking one of these. And because of the way that they're designed, they do a lot of side scraping of the borehole. And so you get poor depth control, you get poor volume control oftentimes with these, and the accuracy of your sampling can go down. Because of the side scraping that happens, if you do use these, you want to make sure that you're careful to discard the very upper part of the samples, because typically we're not looking at those being full of a little bit of whole slough that comes down into the bucket, or side scrapings that really aren't from that particular depth of your sampling. But one of the things I find advantageous with the use of these particular devices is oftentimes rapidly getting myself to a desired depth that then I will take a core sample from using a core sampling device. And so a bucket auger, for instance, might get me down through a gravelly layer pretty quickly that I can then take a core sample below that, or a hard pan or something else that's really difficult to get through. By pressing a core sampler in, I can use one of these devices to get me through some of those sometimes to a desired depth. Then I can take a good core sample. And so use these judiciously, but be aware of the fact that you're introducing some errors in depth and volume control and other things. How many samples do you really need? Matt, how am I doing on time here?
Well, we're quite a bit over.
Oh, we are. Well, somebody should yell at me. I'm not paying attention.
Are you close, Grant?
Yeah, this is good. 15 to 20 cores in a representative area, no more than 25 acres represented by a composite, and then riffle sample or riffle split. And I don't know if you're familiar with these, but you pour the sample in your composite sample, and part of it goes one way, part of it goes another. And you can separate the samples really easily and reduce the volume and get an accurate subsample that then goes 6 to 8 inches for most agronomic recommendations are desirable. But if you're talking about organic matter changes, I'm sure Matt and Jennifer will talk about this in soil health and other situations about sampling for these particular organic matter and other things.